Well, hello again. The rates of chemical reactions vary widely. And as you learned in class, perhaps the three most important controls of the chemical reaction rate are sort of listed here on this piece of paper. The concentration of reactants obviously controls the frequency of collisions between reactant particles. The temperature, an important control, affects the vigor, the energy of those collisions. And finally, the presence or absence of catalysts, special ingredients that reduce the activation energy, can also have a profound effect on that reaction rate. Today we're going to investigate the effect of changes in concentration in a single replacement reaction. Here, then, the basic reaction between hydrochloric acid and magnesium metal, a single replacement reaction. I've tried to diagram there kind of what is going on. The covalent bond between the hydrogen and the chlorine shown there using our dot diagrams, and then the two valence electrons on magnesium, which I've tried to indicate there. And what happens when the two interact is that the two valence electrons on magnesium leave the magnesium atom. They attach themselves to the two hydrogen atoms that leave the HCl bond, and we're left then with the products, magnesium chloride in aqueous solution, the magnesium cation and the two chloride anions, and the hydrogen gas, which evolves as a result of the single covalent bond that forms between the two hydrogens, each with one of the electrons from the magnesium. And then that H2 gas then is the product of the reaction, and we're going to be able to visually see the difference in the reaction rates by using two different concentrations of hydrochloric acid. Set up here behind me or in front of me or wherever the heck it is two gas collection tubes, one of which contains relatively concentrated hydrochloric acid, 6 molar, and the other contains a relatively dilute hydrochloric acid, about 1 molar. Here on the bench top are the two little pieces of magnesium that I'm going to use. I'm going to insert those into the gas collection tubes at the top. I'm going to put a stopper on each one, and then I'm going to invert the tubes into these large beakers of water. The acid, which is now at the bottom of the tube, going to flow down to the magnesium ribbon and start the reaction. Hydrogen gas going to be produced, and the rate of bubbling should then indicate to us the general rate of the reaction. It'll take me a minute to get both of these going because it's kind of a fiddly operation. I'll start with the dilute solution of hydrochloric acid. I'm going to take my piece of magnesium. I'm going to insert it into the top of the gas collection tube, fit in the stopper, and now I'm going to pull it out of the burette clamp, invert it, and put it in the beaker. The water then flowing down, the acid flowing down, the magnesium right there at the bottom. Pull that up just a little bit so maybe we can see it a little bit better. Going to do the same thing with our more concentrated version. Put the stopper on it, invert, put it into the beaker, and attach it as well. And now we're simply watching, waiting for the bubbling that should occur as the acid goes down and starts reacting with that magnesium ribbon. I don't know if you can see the actual piece of magnesium in the beaker there in the gas collection tube. It's kind of hidden by the wrapper there that's shown. And we're waiting then for the acid to make its appearance down there at the bottom. As we speak, it's flowing down the tube, and hopefully any second now we'll begin with our hydrogen gas production. Looking very closely down there at that, we're seeing not much going on there. In the 1 molar solution there, as I peel back the label, you might be able to see some very, very, very faint bubbles of hydrogen gas. Here as yet to take place, but we can see some of them coming up in the gas collection tube. And so as we wait for the reaction to get going a little bit more vigorously, again, to remind you, the single replacement reaction there between the two components. The more concentrated acid then should, as it's beginning to do so now, produce a much more dramatic rate of bubbling than the other one. You can see here the bubbles forming and rising to the top of the tube where they're collecting. Similar things going on over here, but in general a much slower rate of reaction, as befitting the lower concentration of the acid. Now the bubbling starting in all seriousness here on this side. You can see numerous bubbles forming, and if I sneak in really close, you can almost see the bubbles from the magnesium ribbon there right below that label. The gas sort of filling the tube and the gas accumulating at the top. Much, much, much smaller bubbles and a much slower rate of the reaction taking place in the tube with the more dilute acid. Once again here, vigorous bubbling and rapid collection of the hydrogen at the top, as opposed to here in the more dilute solution, much smaller bubbles, fewer of them, and as a result, less hydrogen gas accumulating in the top of the gas collection tube. Give it another minute or two to just confirm our observation there. The dramatic bubbling, the entire tube filled with large bubbles of hydrogen gas, and a rapid accumulation at the top, whereas a much, much, much more subdued reaction taking place in the dilute solution. Makes sense, huh? The greater the concentration of acid, the greater the number of collisions between the acid and the magnesium, and the more rapid products then are formed. And in this case, since the product is a gas, it rapidly then collects into large bubbles, and those large bubbles then evolve up the side of the tube and collect at the top at a rate much greater than the more dilute solution, where there are fewer effective collisions. If I use the same exact amount of magnesium for both of the reactions, I should end up with the same amount of gas in both tubes, but the more rapid rate using the more concentrated acid, resulting in a much quicker reaction as opposed to the more dilute solution. For the last time, I know you're getting tired of this, there the very tiny bubbles being produced by the dilute solution, and here the much larger bubbles produced at a rapid rate and a much greater accumulation of gas at the top.